Hi, this is Carol from the Academic Resource Center doing a workshop on equilibrium for chemistry. Okay, so let's start with what equilibrium is. Equilibrium is a state where the concentrations of the reactants and products no longer change with time. This doesn't mean that there is no movement between the molecules in the reaction, but simply that the rate forward in the reaction and the rate reverse of the reaction are the same, and all reactions are reversible. Equilibrium can be used to tell which direction a reaction will shift, so this can mean either towards the reactants or towards the products. And the amounts of products and reactants can also be obtained through equilibrium calculations. And we'll go through some of these calculations a little bit later in the next slides. Okay, so how do we write the equilibrium constant? We denote the equilibrium constant with big K, and sometimes you can write the subscript EQ as well, but for simplification you can just write K. And basically the equilibrium constant is equal to the ratio of the concentrations of the products over the reactants. And these are the concentrations at which equilibrium is reached. So in general, like I said, K is equal to the products over reactants. So in this case, we have an example of N2 plus 3H2 goes to 2NH3. So our product is the ammonia, NH3, and whenever you have a coefficient, that becomes a exponent corresponding to that chemical in the equilibrium ratio for products to reactants. So here, ammonia has a coefficient of 2, so that's why we see in the numerator, for ammonia, it's raised to the second power, and then for the reactants, the hydrogen gas has a coefficient of 3, so we see that it has an exponent of 3. The nitrogen gas it just has a coefficient of 1, so that's why we see it's just raised to the first power. So in general, if we were to have a reaction with reactants A and B with respective coefficients little a, little b, going to products C and D with their respective coefficients little c and little d, we would write the equilibrium constant K as C raised to the C D times D raised to the D over a to the A times B to the B. And again, just to reiterate, for this, the brackets indicate that these are all in concentration, so that's moles per liter. It's really important to make sure that when we're writing the equilibrium constant that each of the products and each of the reactants are all in the same units, and for these equilibrium constants we're using molarities, so that's moles per liters. Okay, so what can we do with the equilibrium constant? The magnitude of K will tell us how far a reaction will proceed to the products at a given temperature. So if we calculate the equilibrium constant and we get a very, very small number, typically a number times 10 to negative any exponent that's really small, this means that at equilibrium the system will favor reactants, and therefore the reaction yields very little products. Whereas if we have a very large K value, this means that at equilibrium the system will yield very little reactants and instead favor products. Okay, so when we're talking about equilibrium, sometimes if we're looking at a system and we want to first determine whether or not the system is at equilibrium, when we're calculating this value, we call this the reaction quotient Q, and by calculating Q, it will tell us whether or not the system is equilibrium. To calculate Q is very similar to the same way that we calculate K with products over reactants, but we just simply call this Q instead of K because we're not sure yet whether the system is at equilibrium. So once we calculate the Q value, we compare it with K to determine which way the system has to shift in order to achieve equilibrium. So when we calculate Q and we determine that it's greater than K, this means that at this time the system has more products than reactants, and the system needs to shift left in order to achieve equilibrium. This means because since the numerator is greater than the denominator, and since products is over reactants, we need to shift left, so basically increase the concentration of reactants in order for the system to achieve equilibrium. Similarly, if Q is less than K, this means that at this time we have more reactants than products, and so the system needs to shift to the right in order to achieve equilibrium. Therefore, This means that we need to reduce the amounts of reactants that we have and create more product in order for the system to achieve equilibrium. And then if we find that Q equals K, that means that at this time the system is already at equilibrium, so we don't need to like shift any direction to achieve equilibrium since we're already at it. Okay, so like I said earlier, to calculate the reaction quotient Q, it's the same way to calculate as calculating K. So we have products of reactants, and then for a general reaction, A plus B goes to C plus D. This would just be C times D over A times B, the concentrations of those products and reactants. And again, if either the reactants or the products have a coefficient, we need to raise it to that coefficient with the respective product or reactants. Okay, so let's look at an example problem. For gaseous methane and water were mixed in a 0.64 liter flask at 1800 Kelvin. At equilibrium, the